Okay, let's make a start. So, today we're going to talk about language models, okay? And we mean a very particular thing in the sense of language models. We don't mean just models of language. Really what we're talking about is computational models that will be able to tell you if a sentence is good or not, okay? And I want to be as indistinct or not a very clear notion of what good actually means, because that's what we're trying to do. We're trying to get something that, given a sentence, you like to be able to say, yep, that's a good one, that's a good example of English, that's a good example of German, or something like, that's not a very good. Or much more importantly, the sentence is better English than the other. What exactly do we mean by that? Okay, well, supposing we have a sentence like, this is a pen. I assume that all of you agree that the sentence, this is a pen, is a perfectly reasonable English sentence. Okay? Well, pen that this is not a perfectly good English sentence. There may be circumstances where that second sentence is okay, but it's pretty weird or rare. But in general, the first one is much better than the other. I would like a classifier, a computer program algorithm that I can give one of these two sentences to, and it will give me a higher score for the first one than what it will do for the second. You might think, is this just one of these funny exercises that professors give us that's a complete waste of time? And the answer is no, we give other things that are a complete waste of time. But here, being able to tell whether a sentence is good or not is incredibly useful to almost everything we do in natural language processing. We're often generating or choosing between different options, and we'd like to know which one is the most reasonable. We generate all these questions from a Wikipedia article, and we'd like to know, well, which ones of these are the most reasonable questions? Which ones sort of follow the grammar or are most question-like when we're actually doing it? So let's take the next one, and imagine just for a minute that you don't know how to speak Chinese, okay? Apologies to the people in the audience. Actually, I'm going to call on the people in the audience, both of you, who don't speak Chinese, and ask them questions in a minute. Okay? So here we have a Chinese sentence. Please, if you speak Chinese and you understand what it means, don't translate it yet. I'm going to ask you something about that. And here are 4 possible translations that come out of our machine translation system. Okay? So all of you who don't speak Chinese now know sort of what this sentence is about. Okay? But the point is, all of these are ever so slightly different. Okay? And some are better than others. So we're going to use your filters as English speakers to try to identify which of these 4 sentences are the best English. This is independent of what the meaning of the sentence is. Okay? We're going to naively believe that all of these sentences capture the meaning, and they mostly do. Okay? So what I'd like you to do is, especially those of you who do not speak Chinese, okay, to look at those 4 sentences, read them to yourself, and decide which one of these is the best sentence and which sentence is one of these is the worst sentence, independent of what the Chinese actually says. So he briefed 2 reporters on the chief contents of the statement. He briefed reporters on the chief contents of the statement. He briefed 2 reporters on the main contents of the statement. He briefed reporters on the main contents of the statement. Okay? So, 1, 2, 3, 4. Hands up if you think 1 is the best. Hands up if you think 2 is the best. Hands up if you think 3 is the best. And hands up if you think 4 is the best. Okay? So, if we had a computer program that involves judging quality of English sentences, and it involved printing it on the screen in front of 100 graduate students and undergrads at CMU, we now have this computational function that does it, and if we took the most likely one, the one that most people voted on, everybody likes the last one. And I agree, it probably is the last one. Can I ask somebody what they dislike about this one? Chief contents, you think it's a little weird to talk about chief contents. Main contents, it's got the same meaning, but it's just not quite right. Okay. The two is a little weird as well. You don't brief two people, you just brief people. Okay. Now can I ask somebody who speaks Chinese which sentence is the best translation? Wait, we don't have anybody who speaks Chinese? All right, maybe we don't have anybody who speaks Chinese. Somebody, please. Which sentence is the best translation? Four. So it is actually a translation. It's the output of a translation system, and this is typically what translation systems do. Is you basically go, it's something like this. Here's a bunch of words, and you've got to be able to have some function, some program, some algorithm, some Python program that you can run that will give you a score of which one is best. So let's think about that. How we would go about writing a program that would tell us whether a sentence is good or not. It would give us a score that would match what you people think when you're looking at it. Anybody have any ideas how to do this? What sort of things are relevant? Oh, amazing what happens when it's freezing cold outside. Nobody's awake, nobody can remember anything. So it's all got to do with the number of capital letters that are in it. Is that right? Okay. Well, what do you think is relevant?
You want to have like an adjective, but like also you want to record like what kind of nouns that go with the adjectives.
So it'd be a good idea to know something about the relationship between words. There are certain words that go together, certain words that don't, and you want to know. So you can't really have things like a happy chair, probably. It has to be some sort of animate thing to be happy. You can have a happy dog and a happy person, but a happy chair is weird. And so you'd like to know something about what are the relationships, what's the expected relationships of words, and that's something that we're going to try to work out about. Okay? Now, before we get into some of the math today, I'd just like to have a brief overview of probability theory, and partly to do with some of the expressions that is going to appear in later slides. You should be familiar with probability theory, so nothing on that slide should be really surprising to you. Okay? If it is, you probably want to go and read a little bit more about probability theory, because we are going to depend on it quite a bit. Okay? So the things that I want to remind you about is that we have these things called random variables. It's a variable that's got some probability distribution. So I can have a random variable that represents a word. And what you would do is you can ask that variable what its value is. And if you keep asking it, you should get words that effectively cover the distribution of the language, because so they should appear a lot. Okay? And my favorite low frequency word, Nebuchadnezzar, a king in Mesopotamia a long time ago, should not appear very much because it's very rare. Okay? So capital X refers to a particular random variable, and saying that capital X equals lowercase x, we're saying that this random variable takes x, a particular value, or chair. Okay? P of small x is shorthand for the same. P of capital X is a distribution, so it's a distribution, so it's not the probability of a particular word, it's the probability density function over all of the possible words. We can have joint probabilities, so we can talk about the probability that x, the distribution of capital X is some particular word, and the distribution of some capital Y, some distribution is Y. What's the probability of both of these? They can be independent, okay, or not, okay? So some things, probabilities are independent, and some things are not. So, for example, of something where probabilities are not independent is supposing X was people's first names and Y was people's family names. Okay? Do you think that probability of X, probability of Y are independent or in some sense linked to each other? So if I have a distribution of everybody's first name and a distribution of everybody's family name, and I randomly pick from each of the distributions will I get a name, a proper name, that could be the name of someone, or will I get an unusual one? Yes? No? Yeah?
They probably have to be independent, not independent because if you're from a different culture, you probably have different last names.
Correct. Okay, so they're probably not independent, although admittedly in America you do get interesting distributional things with people in second and third generation from different cultures. So it's not that unusual in the US to actually find out that there are people called, you know, Jose Chang, okay, where you have a Hispanic and a Chinese name. That can happen, okay, and especially in California. But in general, it's not that they're independent, because usually the person who gives parents who give the first name of someone are from some culture, and therefore they're going to follow it. And yeah, they might bubble up to an utterly generic, non-cultural name, but they're likely to do that. But if it is a cultural name, then it's likely that the other name. So these are not independent, okay? And so sometimes things are, and sometimes they're not. And sometimes we don't have enough data to know, and so we just assume they're independent, which is often bad, but it's easier to do. So we do it, and we feel guilty about it. Well, just a little guilty about it. Okay? We can have conditional probability, which is different, is given a choice that y is some particular value, what's the probability of x? And again, let's go down to the proper name. If I tell you that the family name, okay, is Chang, okay, you can guess something about the distribution of what the given name is, okay? It can still be David, okay? Actually, I know somebody called David Chang. Okay, he's a professor at Notre Dame, okay, but it's probably not going to be, you know, Sai Krishna, probably, okay. It could be, but it's less likely to be. But while if I give you a proper name that's like Narayanan, a standard Indian name, then Sai Krishna is a possibility as a given name, and it's going to be a higher one than Jose. Well, David, it could still be David as well, especially if it's an American name. So these are just, I want to remind you about that. If you're not familiar, please go and look these things up because we're going to refer to them. So the first thing we're going to do is we're going to talk about Unigram models. So Unigram models is, let's look at the distribution of words. Okay? So which words are more common in English than others? Okay? And so give me a word that's very common in English. The. The is the most common word in English. Okay, so if you look at any reasonable sized corpus of English, the most common word is the. Does anybody know its frequency? That's really geeky to know that. You do, and you're not going to admit it. It's about 3 or 4%, which is quite a lot. 1 in 20, 1 in 25 words in English is the. Can you give me a really rare word in English? What was that?
Abstracted.
Abstracted. So abstracted is not a very common word. It's definitely much, much further down the frequency table than the. Okay? And now what I'm going to do is I'm going to take the word abstracted. I want somebody to give me a word that's more frequent than abstracted. More frequent. More frequent. Do you have a big vocabulary or not? Yeah, I think so. You think so? Frequent is more common than abstract? I think it probably is. Okay? And now I want you to give me a word that's less frequent than abstracted. Do not give me infrequent.
That's kind of fun. Esoteric?
Esoteric. Excellent. Okay? I think esoteric probably is further down there. We've got intuitions about what these distributions are, but we don't actually know. Okay? So, you know, we've got a good idea here that we can put things on a line of frequent to less frequent, but if I keep giving you them, it's going to get harder and harder and harder to do that, because you probably don't carry around a frequency table of words in English. This comes to this Unigram. Unigram, okay, is what we do is we actually do look at all the words in the language and we calculate what the frequency is. We take a very big list of words, take all of the newspaper, all of Twitter, all of what Google indexes, that's a lot of data, okay? And what we do is we try and work out the most frequent words and the least frequent words. So for every word, we find it duplicates, we sum it up, and eventually we discover that is way up here, okay, and esoteric is way down here, and there's other ones way down there that are just ridiculously infrequent, including weird spelling errors and words that are not words, because they're actually your password, but Google didn't know that when they were indexing. Okay? And so we have that, but we can calculate that, and we sum up all the words, and we divide the frequency by the number of total words, and we'll get a probability. And the sum of that will hopefully come up to 1 as long as we've got a reasonable machine that we're calculating the numbers from, and it can deal with really tiny numbers, but let's ignore that. But we can get a model of that for English, and we could get it for all of English, but realistically it's going to be hard to get it for more than all of the documents that Google have, because if you think that's not all the documents in the world, but it's about as close an approximation as you're ever going to get, okay? And it might be all the important documents in the world, because if Google can't get to it, you know, it's not real. But we can do that, okay? And so then what we could do is, given that distribution, okay, as we have this big distribution, there are some number of words in here. I'll come to that in a minute about how big that might be. And then we have this dice, okay? Actually, technically we have a die because there's only one of them. So we have this dice and we throw it and it's got 100,000 edges on it. Okay, so it rolls around and stops. And whatever it stops on, it's basically telling us a frequency, and we're going to pick the word that's at that frequency, that particular form. It's better to think about it as we're going to get a random number between 0 and 1, okay? And what we're going to do is, given the order of all of our words, okay, what we're going to do is take whatever the probability is, and we're going to look to see, summing up from the left or right, it doesn't really matter, where we are in there, and we're going to select some probability, and we select a word that's more probable. Because the is going to have more probability mass, okay, than esoteric, throwing the dice 100 million times, we're more likely to get the than we are going to get esoteric. But the words that get generated are going to have the same probability distribution function. It's what the real corpus actually has, okay? So that's what we want to be able to do, okay? And so let's have a look at what some of these frequencies might be. Okay, so this particular corpus that was calculated is 3.8%, okay, 0.038. Okay, the next most common one is off, then and 2 is in for. All function words in English, because they're the ones that actually happen the most. They're the ones that appear multiple times in almost every document. Okay, and then when we get further down in rank 1000, we get words like joint, relatively, plot. And then we get del1 subseq, we get rule, we get 62.0, we get 9.1, and we get evaluated. Okay? This document, this data that we actually calculated from, what can you tell me about it? Do you think it's a newspaper?
That's not what I was going to say.
Oh, right.
I'm assuming that all of the things that appear on the right-hand side, they're exact ones.
Yes, notice how all the probabilities here are exactly the same, so they probably appeared exactly the same number of times. And remember, when you appear the same number of times, it's going to be an integer, but we'll come to that. And so it is that they appeared only once or twice or 3 times or 4 times, but it's a good guess that they only appear once, okay? And so you can actually get some information about that. And if you did a quick calculation of what 1 divided by 0.00014 is, and see what you get the nearest integer to, you might be able to say it was a 32,117 word document that you calculated it on, or some multiple of that, which might be true, okay? But do you think this was calculated on newspapers? No. What do you think it was calculated on? Journals, yes. This seems to be overly technical for most of our newspaper readers. It's probably not children's stories, and so it's something else. And all of these words seem pretty technical. In fact, they seem pretty technical even in our area. And so it's on some set of papers, journal papers, or something like that. which means that the distribution of these things depends on the data that we're actually dealing with. Now, if we did take newspapers, I wouldn't be surprised if the top 10 would be exactly the same, but I'm pretty sure once you get down to 1,000, it probably wouldn't be. Okay? We can take this Unigram model where we look at the frequencies of particular words and generate from it. So what we can do is take that model, we can throw our dice, we can choose which of that distribution it actually is. So what we want to do is 3.8% of the time we want to generate the, whatever the next one was, 2% of the time we want to generate off, and 0.00014 probability of the time we want to generate joint, or whatever it was. And if we do that, we get this paragraph with some bunch of random numbers. So you get first from less the this different 2004 close parentheses comma. I'll come back to that. Out which goal 19.2 model with their LT tilde I question mark 1. Yeah, okay. And it looks like utter nonsense. Okay. This you can agree is got a bunch of English words in it and some math and some markup or something in it, but it's basically nonsense. It's got no coherence whatsoever. Now remember when I asked what would we actually care about in a language, and somebody, I think you down the front, said we should care about the co-occurrence of words next to each other, because happy chairs are very rare, okay? Happy dogs are not, okay? So happy dog as a pair is much more likely than happy chair, okay? Even though I might have said happy chair more in this lecture than I've said the other one, okay? But let's ignore that, because so what we could do is, instead of look at singletons, okay, we could try to look at more history. We try to look at longer sequences. And so what we could do is, instead of looking at single words, we could go to the other extreme and look at whole sentences. So what's the probability of this sequence of words? So if I give you a sequence of words, what's the probability out of all sequences of words that that actually happens? So if I say, how much is the dog in the window, okay, that's going to have a higher probability than a dog in the window that is much higher. Okay, it's the same thing backwards. Okay, which again is going to be very rare apart from in my lectures, because it's my example of something that's very rare. But how much is the dog in the window over all of the text in Google is going to be fairly common compared to window being dog that is much higher. So we could calculate for every single sentence. What we could do is we could work out what its probability is, and there really are some sentences that appear multiple times, okay? So sentences like yes, or no thank you, or can I have another beer? All of those are actually going to appear much more often than other sentences that may be perfectly reasonable sentences, but they only appear once. Okay? So what we could do is look at all the sentences that are there. We could calculate the likelihood of each sentence, and then what we could do is we could then do our, again, probability again, but do it on the sentences, the strings of words, rather than on isolated words. And if we do that, okay, we get this, okay? Bill Clinton's unusually direct comment Wednesday on the possible role of race in the election was in keeping with Clinton's bid to portray Obama, who is claiming to become the first black US president, etc., etc. This is well-formed English. But of course it is. It's a probability of that particular sentence, and that sentence already existed. It appeared in some newspaper, probably 10 years ago. Okay? So this is good. We get a probability. We get much more reasonable sentences out of it. But we have the problem of, what do we have the problem of? Well, this is only going to be able to give us probabilities for sentences we've already seen. So imagine if we went through life now and said, that's it, you're never allowed to come up with a new sentence, ever, okay? And the only thing that you can do is use sentences that have already actually existed before, okay? I think it's possible to communicate like that, but I think it's incredibly stupid to do that, okay? So in other words, you can't suddenly have a new president, because you now can't say something like Homer Simpson is the president of the United States, unless that sentence has already existed. Well, maybe it has already existed, you know, it's possible, okay, that somebody said that before, okay? But some new person that we don't know who isn't even born yet, okay, in 50 years from now they become president of the United States, you would never be able to say that sentence, or at least we wouldn't know what the probability of saying that sentence is. So it's sort of, you know, the Unigram one is too open, and the sentence one is, well, we just can't get enough estimate for things that we've never seen. So can we do something in between? Okay. So we introduced this notion of an n-gram model. N is going to be an integer, and it's going to be a relatively small integer. N-gram, a unigram is a 1 gram, and a bigram is a 2 gram, and a trigram is 3. Okay. And then after that, people are never very sure whether they're called quadrigrams or whether they're called 4 grams, and people sort of argue about it, but either of these are fine. And so what we can do is, instead of looking at the whole sentence, we could say, given a word, and given its n words previous, 1, 2, 3, or 4 more, okay, how does that affect probabilities? Okay? Now, this is a good thing to do, okay? It captures this thing of co-occurrence of words, and the longer the context, it should be the better, but the more data you actually need. Okay, I'm going to take a little break from this part, and I'm going to ask you something about how many words do you know? Oh, that's 2 words. 3 is the other word. 4 is another. Oh, that's not going to work. How many words do you know? Okay, so it's probably true. Okay. So how many words do you know? Okay. So hands up if you think you know 1,000 words.
These are exact.
Completely ambiguous, okay? 1,000, only 1,000? No, at least 1,000 words, okay? You all know at least 1,000 words, okay? Or especially if you put your hand up, because you probably wouldn't understand it. Yeah. Okay, so let's get bigger than that. Let's say 10,000. Hands up if you know 10,000 words. You all know 10,000 words, okay? You all know 10,000 words in English, okay? Even if your native language is not English. Okay. I'm currently talking about English. I'll come to the bilinguals in the audience in a bit. Okay. Hands up if you know more than 100,000 words. Going to make you name them. You probably do not know more than 100,000 words. Okay.
What are we counting as a word?
Excellent question. Okay. Because it's really confusable. Do we include things of uppercase, lowercase? Do we include walk, walks, walking, walks, okay, walkingization-ism, okay, as a word, okay, and the answer is yeah, if you want, okay, and then when we start going into other languages, it gets much harder to actually decide what a word is. We talked about morphology in the last lecture, and so you get these variabilities in sort of one word with different forms, okay, if you speak Chinese and nothing else, ni hao, when you speak Chinese, you don't put spaces between words, okay? So where are the words? But don't worry, if you speak English, you also don't put spaces between the words when you speak. So you're actually quite used to this idea that there are no explicit word boundaries. But it's a good question, okay, of which there isn't a particularly good answer, apart from make some reasonable decision, okay? Your vocabularies are probably somewhere around about 20 to 30,000 words, okay? If you're non-native in English, it's going to be less for English because there's certain words that the native people will know and there's certain words that the non-natives will not know, okay? And although we probably know all the computer science terms equally, it's probably the case that if you name things in a kitchen, you've no idea what they are. But realistically, I grew up in Scotland and I can't name the things in the American kitchen properly. I don't know what the local names are, and I always get it wrong. And I have to go to Target and go, I want one of these because I don't know what they're called. We have different distributions about what we actually, but probably college-educated people have vocabularies in the regions of 20 to 30,000. If you're college-educated in the arts, in linguistics, in English language, your vocabulary is probably bigger. Okay, could be up to about another 10,000 bigger. Okay, if you're bilingual, okay, you probably also know about 20 to 30,000 in your other languages. Okay, so there's a lot of words like that. But if I got all of you to write down all the words that you know, okay, although there would be a big commonality between you all, okay, there would be way more than 30,000 words from all of you, okay, because we all know different things about different things. Some of you know all about musical notation and know all the words from music. Some of you all know about fixing bicycles, and some of you actually know all of the Pokemon characters. Important things, okay? And so we would get, I don't know, there's probably 30,000 Pokemon characters. In another project I'm working on, it actually explicitly came up about the number of Wikipedia articles for Pokemon characters and whether they're allowed to have their own Wikipedia article or not. Okay, this was not for doing question answering in our NLP class, but it was a serious question and how people argue about it. But we have a bigger vocabulary if we take the union, and so if we want to actually calculate what the probability of a word is, we sort of have to make a decision about what our vocabulary list is going to be. And that's quite hard, okay? If I got you all to write down all the words that you know, I can pretty much guarantee that some of you will make typos when you're writing down the words. I will. If you don't, I will. Okay? And therefore, we're going to have some typos in the list, and it might even be hard for you to know whether they're typos or not. Okay? I can name some Scottish villages that none of you have ever heard of, and none of you will be able to say, in fact, it all looks like an encoded password, but it's still a Scottish village, I promise. Echolfechen and others, although that's in England. But we need a size, okay? So I'm just going to say 100,000, okay? And what we're going to have to do is we're going to have to deal with anything that comes after that we're going to ignore, which isn't the right answer, but we'll come back to it. But if we did do 100,000, okay, and then what we were wanting to do was we wanted to collect statistics on looking at the co-occurrence of bigrams, so one word followed by the next one, okay, for 100,000 words, we need at least how much data to be able to try to estimate what the co-occurrence of green table is versus happy chair, okay? We're going to need quite a lot of data to do that. 100,000 words at least, we want one occurrence of each, but that appears much more often than esoteric, so I'm going to need a lot more so I get at least one occurrence of esoteric, okay? Then I want occurrence of esoteric with all possible other 100,000 words, okay, or maybe 9,000, well no, 100,000 because we have to care about what's the probability of esoteric, okay? And the answer is 1, because I just said it, and that's about the only time it's ever been said, okay? So I need a lot of data to try to estimate this result. But hey, I'm Google, I've got a lot of data, I've got a lot of machines, I can actually calculate all of this. So if I do calculate all of this, and then care about my generator, okay, I get something like this. So I'm now caring about generate a word, okay, and then I'm going to generate what word comes with it, conditioned on what the current word is. And then I'm going to the next one, and next one, next one. So I don't have long chains, I only have this bigram model. And so now I have EA 33, A34, A5 models are also being completely surpassed in performance on drafts of online algorithms can achieve far more. So while substantially improved using CE. Now, I read papers as bad as this, okay? This is not English, but it's much better than the word soup that we had in the Unigram one, because there's some connection between these words. So, are also beam completely, okay? This continues, with supervised. All of these are more likely than just being random, so we're getting something that's better, okay? We're getting a better estimate of what the language is actually like, okay? So this is cool, and that was bigrams. So we could do trigrams, okay? So we could actually try to go further and go to trigrams, and then we get a model like this. Garbage, 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 garbage. Then we get these equations were presented in both cases. The scores something into a probability distribution is even smaller, r equals 0.05, and this is exactly something during something is gradually relaxed. This approach, there's little bits of sense in that, there's little bits of reasonable distribution in that, and that's useful. Because we've gone to 3gram, we're caring about 2 words in context and predicting what the next one is, and we're getting some context when we're actually doing it. There's still nonsense here, it's not all right, okay? But as we add that greater context, we get a better representation. So more context helps. We saw that when we used the full context of the sentence, we got full sentences, but we couldn't deal with sentences we'd never seen before. I'm pretty sure these sentences have never been seen before, but they're sort of better. So maybe what we could do is, given our sentence, window the in dog that is much how, what we could do is we could measure what the frequency is of each of the trigrams in it and use that as a score. While if we take the frequency of the trigrams in how much is the dog in the window, we should get us probability a higher score for how much is the dog in the window compared to a window the in dog that is much higher. Okay? That's what we're trying to do here. That's what we're trying to get some algorithmic way to be able to score better sentences over not so good sentences. Okay? And it looks like that just looking at the words in context may give us some way of measuring how much better they're actually becoming. Now, let's go to your question. What's a word? Okay? Is punctuation a word? Do you think it makes a difference of whether the previous word was a comma or not a comma? Makes a difference. So we probably want to care about punctuation. Okay? So we probably want to treat punctuation as a type of word. So commas, periods, question marks, etc. are all something we should care about. Okay? Now, also let's talk about speech. I know we're primarily talking about text here, but let's talk about speech. So in speech, what actually happens is people don't speak fluently all the time, okay, unless they're being prompted and reading a teleprompter, or they're on TV, or they're really good at speaking. There are some people who can do that. I'm not. And so when people are speaking, they often use what are called fillers. Okay, and they say, well, I'm going to talk about, and they use and and they sometimes use words in that as well. So they'll say so, or they'll say well at the beginning of a sentence. If you want to frighten people, for the rest of the day, look at what everybody says to you, okay? And if they start a sentence with so, they're a computer scientist. Because we do. So, and it's just true, actually engineers as well, so it's a fairly broad thing. People who are trying to sound knowledgeable will use so at the beginning of a sentence while they're thinking, because they're trying to say, I'm thinking of the consequences of the information that you're actually telling me, so I can suggest, let's go for lunch because I'm hungry. But we use these words, we might use well as well, but so is more engineering, right? We also make errors when we talk. And actually, most of the time the listener doesn't hear, because the listener just self-corrects and gets rid of it. If it's extreme, people do notice. But when people go, I want a Coke and a ham sandwich, they don't remember that the person said, I want a Coke and a ham sandwich. They don't remember that it was repeated 3 times. Okay? Because we don't. Our brain's actually very good at cutting that out, such that you absolutely can't remember. Because people do it all the time, and it would be superfluous to us understanding, so our brains have learned to be able to cut that information out. And then the question is, should we include that type of word, and do we have to decide how to write down the word okay, which goes in there when people are actually thinking, is it a UH, is it a HUH, is it a UHM, is it a UHN, okay, and that can get very hard to do because it's none of those, okay, it doesn't have a written form, okay? But maybe we should include those too, and if you're doing speech recognition, you have to include these too, because they really do exist, and people really do say them, and they appear only in certain places and not in other places. Okay, hands up if you're Californian. Aha. Okay, sorry, it's not that I'm picking up. Well, I am. Do you ever use the word like?
A lot.
like, you know, like. So in English, and I'm just picking on the Californians, but I would like to buy that. Everybody else does it too. Okay. So they use the word like a comma, and it gets put in and inserted, and it only can be put in certain places, it can't be put in everywhere. If you're doing speech recognition, you really have to care about people saying like, okay? Because it's important, okay? There are other things that happen in speech, and hands up if you speak Hindi or some northern Indian language, Marathi, etc. Okay, so when somebody's talking to you, you're quite likely to respond acha, which basically means yeah, and it's a response, okay, and people do it all the time, and actually in the UK, Indians do it. It's notable that Indians do it. While doing it here, people go, what did you say? Because they're not quite as familiar with it. But there's often these word thingies that appear that you have to work out how to use them and deal with them in language. So the definition of a word is really hard, okay? But you have to make a decision, because we have a programming language here and we're going to assign everything to a particular word, okay? Independent of anything, okay? So we just have to do that. It might not be right, but if we've got enough examples, we can probably do something about it. Okay, so we talked about Ngram models. Do you think that they know English? No. Do you think they understand English? No. Okay. Do you think they're artificial intelligence? Well, because they don't have neural nets in them. Is that the only way they're artificial intelligence? So I think you're right. They don't know English. They don't understand English. They're just a model. Okay. They're ridiculously useful for being able to do an awful lot of NLP tasks. Okay. And that's cool. And that's enough. They don't have to be sentient beings who come down and make prophecies about what comes next. You don't have to like run your Ngram model to see what it predicts to know what you're going to do next. Okay. Not an oracle. But it's a useful way of measuring whether a sentence is good or not. And it's a way for us to be able to rank sentences from good to bad. Okay? Unknown words. Okay, unknown words. There are words you have never heard of before. Okay? And they're perfectly reasonable words and other people have heard of them. Okay? We talked about names of Scottish villages, and there's a whole bunch of ones that you'll never have heard of before. Okay, what I'm going to ask you to do now is I want you to go back in time 10 years, okay? Just do it on your own personal time machine, okay? And I want you to go and talk to people there, and I want you to come back, and I want you to tell me a word that's used today that was unquestionably unknown 10 years ago. Can anybody give me a word like that today?
Unfriend.
Unfriend. Okay? Way back when I was a little boy, okay, once you had friends, that was it for life, okay? Absolutely, you couldn't get rid of them, okay? Well, you could move continent to North America and away from Scotland, and then you could get rid of it. But no, unfriend didn't exist. I don't know if it was exactly 10 years ago, but it's a good example of a new word that has come into fashion, really primarily in social media, and I think it's a Facebook word, but it might have been a MySpace word, but you're not old enough to know about MySpace. So it's a good example. Do we have another one?
Insta-famous.
Insta-famous. Yes. Yeah, I don't think I hadn't heard that until now. So yes. LOL. Okay. Again, and, I've been on the net for 150,000 years, and I was on the net before the smiley was invented by Scott Fallman here. I don't know if I actually read that message, but it's possible because I was reading Usenet at the time. But LOL was not something that we would actually say. Okay. Brexit. Okay. Brexit. Yeah, you're just saying that to tease me about how hard it is for me. It's trying to kill itself. But anyway, yes. But yes, Brexit didn't exist 10 years ago. Okay. And that's new words come in all the time. Okay. But even Facebook 10 years ago. No, it's a wee bit more than 10 years. Okay. But Instagram, Snapchat, they're all words that we're familiar with now. So words change, and we have to deal with unknown words. And although you can talk about these, big words that everybody picks up, but there's new words all the time, okay, that actually get introduced. So here at CMU, okay, all the buildings have a name. All the buildings have an abbreviation, GHC or WEH, okay, and we all sort of know what they are, okay. But it was only 10 years ago that this building was built, in 2009, so it's a wee bit more than 10 years, and we didn't know what it was called, and so GHC didn't exist as a term that would get used on CMU campus, so you never saw it anywhere, and yet we've introduced it. And then TEPR has got an abbreviation as well, which I don't even know what it is. Is it just TEPR? I met people in Posner Hall saying, where the hell is this room? Okay, and the answer is, no, it's the other side of Forbes, but I don't know I don't know if it's got TEPR Quad, TPQ, or something. There'll be some abbreviation for it. And we'll all learn in 10 years from now, people will go, well, what's hard about that? Okay, language changes, we get new things, but also, I strongly suspect that all of you don't know everybody else's name, and I'm pretty sure there's some names here other people have never heard before. Okay, and names are pretty common. Okay, and yes, there's probably some really unusual names in the room, but even ones that are relatively common within your sphere, other people might not have heard. Okay? So we have unknown words, and so what do we do? Because remember I said we're going to build 100,000 words. What are we going to do for that 100,001th word, okay, that isn't there? So we have to care about unknown words. What's the probability of an unknown word? So imagine you're looking at text, okay? The next word might be a word you've never seen before. And you can give probabilities about that, okay? So imagine you've never heard the word Nebuchadnezzar before, okay? My famous Mesopotamian king, okay? And you never heard it before, okay? And that's an unknown word, okay? And so what do you think the probability of the word Nebuchadnezzar is in the sentence 2 + 2 equals? Probably relatively low. But I'm going to say it. No, I'm not going to say it. Okay? But what happens if I say the ancient Babylonian king? What do you think the probability of me saying Nebuchadnezzar after that? Much higher. There are probably other kings. Not that I know them, but there are other kings. So it's going to be different. Okay? So let's take another one. What happens if I say something like, did you see on the table my red? What next one is? As opposed to the sentence, my name is. Okay? After my name is, you are aware that you're likely going to hear something that you might not find familiar. Okay? Because people's names, sort of, it's their whole point. Names are supposed to be unique or relatively unique, and therefore you're more likely to hear a name that you've never heard before. So your probability of hearing an unknown word will change from the context. So if you had all this data, what you could do is you could go and find the really low frequency words, and you could say all of them are unknown. I'm just going to label them as unknown. If they appear only once, they're unknown. And then you could calculate your stats on what the likelihood of an unknown, we have now a special word underscore unknown underscore that isn't elsewhere, anywhere else, is an actual token, and you can talk about the probability of unknown. And you have to do that, okay, because you'll always get unknown words. We just don't live in the world where there are closed vocabulary things, even though some people think that there are, but basically it breaks everything when you give it. So we really would have to care about unknown words, and we can do this by estimating what the probability of an unknown word is. It's not hard. We just have to take it, it's an object, we have to step up some meta level, and we have to name what these unknown words are, and we can work out what the probability of unknown words are. N-gram models and finite state automata, they're the same thing. What? They're the same thing. Okay? So, this isn't immediately obvious, but after a while it becomes immediately obvious. If you think about bigrams, okay? Bigrams are, you've got some word and you're trying to work out the probability of the next word. That word that was the context, you can think about it as a state. And you've then got 100,000 lines coming out of it, depending on which word you hear next, okay, and you have probabilities next to them. And what you do is you go to another state, and that other state is the word you've just heard. And you don't care about any previous context, it doesn't matter. It doesn't matter whether your previous word was king, or your previous word was, well, your previous word was king, or your previous word was queen. You only care about the previous word. And now you're in this state, and you don't care how you got to that state, you just care about that state. So this means that you can represent a bigram for a 100,000 word vocabulary with 100,000 states. Okay? If you want to go to bigrams, okay, so you're going to be here about 2 words, it's 100,000 times 100,000, which is a big number. Okay? And that's just fine. Although there exist some bigrams that never happen. Okay? That is the case. Okay? I have a list, but every time I name them, I have to find another one for the next time I do the class, so I'm not actually going to name them. Okay? Although I can tell you things about, because we did analysis of Wall Street Journal from 1992 to 1995, because it's one of the standard data sets that we have, and the answer is green table never appears in the Wall Street Journal during that time, and I don't think any of you think that green table is particularly weird, okay? But it never appears. So relatively common things don't actually appear in lots of data, so you should be aware of that. So you can always represent things as finite state machines, and there's other things that you get with that, because you also get things like, ooh, I can do determinization, minimization, I can do various approximation functions on it as well, and sometimes that's useful. Okay. Another thing we have to talk about, in addition to unknown words as a special case, is starting and stopping. I glossed over that. I've not explicitly talked about that, but it is something that's actually important. If we're throwing this dice about when things are not flattening, we also want to know when we're at the beginning, when we're at the end. If we're going to generate a sentence, we have to start. So we really need this special word, which means start. It's the word before the first word in the sentence, if you can deal with that deep philosophical point. There's this special word that appears before every sentence. So if you're doing bigrams, what you want to know is, given the start sentence symbol, what's the likelihood of the next word? Which is very simply, what's the probability of words at the beginning of the sentence? And of course that's different than after some other words. Okay? The is much more likely to appear at the beginning of the sentence, while the is very unlikely to appear after the word the. Okay? So we need a special symbol called start, and we also need a special symbol called end. Okay? Because when we're doing our probabilities, we can stop. And what's the probability that after this word is the end of the sentence? Okay? And we like to be able to calculate that too. We actually go a little bit further than that, because if we're dealing with bigrams, trigrams, quadrigrams, we have to have multiple start states at the beginning to be able to start off. Okay? We usually treat that as the same symbol, but we never calculate probabilities for any of those, because we just always assume there's a start, and then we get into the real world and we have however many starts as we're actually going to need. So we talked about a bunch of different models. We talked about unigrams, bigrams, trigrams, and more, about trying to work out whether they're good at predicting sentences or good at scoring sentences. But we really need a way to measure how good these models are, okay? Because remember, the longer we make the context, the harder it is to find the data to get proper estimates. And you don't have to go very far to be able to start finding significant numbers of rare events. And so you just want to have enough data to be able to predict this, and therefore it might break down before you get the benefit of increasing the length, and you don't get a benefit because you can't estimate it because you don't have enough data. Okay? So what we'd like to have is we'd like to have a way that, given some model, you'd like to be able to calculate with a number about how good it is. Now, it's a little hard to calculate in complete isolation, and so often you want to calculate with respect to a particular data set. So what you'd like to be able to do is, here's a model, here's some data, and you'd like to say, how well does this model predict this data? How realistic is this data compared to the model? So we're going to talk about evaluation. Which model is better? I'd really like to get a number, because I want to know if you're going to work on this cute new neural net technique of building a language model, and you say, well, it must be better because it uses billions of parameters and takes 3 weeks to train, and that must be better than a bigram. And so that's not a good enough reason. I want to know if it's actually better. Okay? So what I'd really like to know is, given some model, I'd like to know what's its probability of being able to generate some test set. So I have some data, some natural data, and I say, here it is, and I'd like to know, you trained in all of Reddit, and we subtracted 10% of Reddit, and that's a test set, and now I'd like to know that the model that you have, how well does it predict this test set? We have a measure, and it's called perplexity, okay? Made up term, well, the word isn't made up, but the term is for this. And perplexity is the probability of the test set normalized for the number of words, okay? So you're going to get a number, and smaller is more predictable, and bigger is less predictable. It just is, okay? We always do that with all the measures that we do, and we do a random direction just to confuse you so we can test you into multiple choice and exam. No, that's not the reason that we're actually doing it. But perplexity, bigger means harder to predict, or less of a match, and smaller is easier to predict or more of a match. This is a formula for it. It's fundamentally got to do with entropy, okay? And if you think about what we're talking about, entropy, if you think about entropy as a sequence of random events, the question is how predictable are these random events, okay? And the more predictable they are, okay, the smaller the perplexity, and the less predictable they are, the higher the perplexity. So let's talk a little bit about what things might have high perplexity and what things have low perplexity. Let's talk about US telephone numbers, okay? I hope you're old enough to actually know what telephone numbers are, okay? But back in the ancient days, we used to call people in things called phones, and we used to type in 10-digit numbers to be able to talk to people, okay? These telephone numbers, okay, can have any numbers from 0 to 9 in them, okay? And they're random. Well, actually, they're not random, okay? Out of the 10-digit, the first 3 are what are called an area code, and there's only a limited number of those, okay? And they're usually cities, Pittsburgh's 412, and some other number that I can't remember. New York's 212, and so you remember these things, and so it's not got all possible ones. So in other words, there's less variability going in the first 3. After that, there is some randomness, but it's not completely random, okay? And the next 3 digits also follow exchanges, and therefore they're maybe limited in what they are. The ones after that are probably pretty close to random. And so if we talk about perplexity for that, definitely it's going to be no bigger than 10, because there's only numbers that can actually come, 0 to 9. There's nothing else. It can't be bigger than 10. I'll tell you why. And so it's probably less than that. But then let's talk about Wall Street Journal, okay? There's a vocabulary of, let's say, 100,000 words. And it's clearly got much more choice on the things that can happen next than telephone numbers. So its perplexity is going to be bigger, okay? I don't remember this, although I think I can derive, because I know what it's trying to capture. If we look at models on Wall Street Journal, we've got Unigram, bigram, and trigram. What we notice is that the perplexity goes down based on the model. If the model is better at predicting, okay, i.e. captures what the distribution is, the perplexity is going to be smaller. Okay, so as we go to trigram, we're down at 109. Okay, different tasks have very different perplexities. So we talk about Wall Street Journal, it's 109, but we talk about bus information, a system that we ran here for years, the perplexities are only 25. And the number, I'll talk about this at the end. The perplexity is effectively the average branching rate. It's a little weird when you think about it, but it's really, given where I currently am, what's the average number of things that can come next over the whole sentence? Okay? And so a bigger number means there's less predictability, and a smaller number means there's more predictability. Okay? So if you think about time and how we give time, it's going to be smaller. If we think about Passwords is going to be bigger because it's much more random, but it's not quite as random as encoded passwords, which really truly are random, okay, which I'll have a bigger course. In the bus information, it's sort of all fixed, okay? People say, I want to go from CMU to downtown, I want to go to the airport. There's sort of phrases that are, yeah, there might be 10, maybe even 20 different ways to talk about where you're leaving from, okay? But there's not, 1,000 different ways of saying where you're leaving from. The confusability or the space of bus information is really the bus stop names, okay? For which there's lots of different ones, okay? There was at the time 13,000 bus stops in Pittsburgh. There's now less than 10,000 because they got rid of a whole bunch of them. Not because we were having problems with speech recognition, so it was high conditional probability, i.e. there's lots of dependencies between things, we get lower complexity. The perplexity is the average branching rate. It's much easier to understand. So the perplexity numbers are usually somewhere between 1 and 15,000 and not bigger than that, okay? And for most language things, I mean here, the Unigram one model is just under 1,000, okay? And we know that's not a really good model, okay? But even then we're getting 1,000. For Wall Street Journal, it's pretty open English, okay? So perplexities don't really get very, very big. And once they get below 10, it means it's maybe not an interesting problem, or it's an easy problem, or you've over-constrained, or are you sure you're doing this right, or maybe the data you're looking at has been generated by some synthetic form, because it just doesn't have natural variability in it. Human languages are not going to have, and human language models are not going to have perplexities of 10, because that's too easy. So what is the probability of an unseen word? I've already talked about this. So what is the probability of a word that you've never seen before? Okay, you do see words that you've never seen before relatively often. And so if you wrote down every word that you heard or read all day, okay, and then marked the number of words that you saw and the number of words that you'd never seen before, okay, it would have a non-zero number. There would be words that you're seeing that you've never seen before. Okay, it might be people's names, it might be the new name of a company, it might be the new name of a product, it might be a misspelling, it could be other things, it might be a new building you never heard of, there could be lots of things, it could be a term that you hear in a class that you've never heard of before. So yes, there's going to be new words, okay? But you don't really want to have a probability of 0, okay? Probabilities of 0 break almost every program you're dealing with. When you want to know the probability of a sequence of things, what you usually do is work out the probability of each, and you multiply them together to get the probability of the sequence. If you multiply 0, okay, to anything, you get 0. So if you get any unknown word in your sentence and you do your multiplication, you get 0 at the end, and that's not very useful, okay? You might be able to sit there and say, yes, that's right, because I've never seen it before, but it's not useful, so you don't want to do that. It is incredibly common to find unknown words. We've done analysis of this, and so for example, again back to Wall Street Journal, because we do analysis on it, how many new words per day appear in the Wall Street Journal that have never appeared before? And the answer is about 3% of tokens, not, of types, not of tokens, so words that I've never seen. But 3% every day appear. Some of those are numbers, and we know there's a lot of numbers, but some of them are just genuine new words. New people who suddenly become famous, new places that suddenly become famous that you've never heard of before, that the Wall Street Journal's never talked about before, but there will be new ones all the time, okay? And you can't just say, I'll have a list of everything. It's not going to happen, okay? So you really, really, really need to model these unknown words, okay? And so we need to know the probability of unknown word given sun off, okay? And of course with sun off, we know we're into probably, not necessarily, because there's some good words that can be in there as well, but we can have sun off somebody's name, and we know that we're more likely to find people's names that we've never heard of before, because it's in the nature of names. Okay. So when we're trying to get our probabilities, okay, and we don't have any examples, how do we know what the probabilities are if we have no examples? Well, we could do this trick which I mentioned before, where you go and find low frequency things, pretend they're all unknown, okay? Maybe everything that appears once, you pretend it's unknown, okay? And you just replace all the ones that appear once with unknown, and you then calculate everything but unknown. But you're sort of giving up the data that's there with these unknown ones. So how can you really work out what the probability of unknown ones are? Okay? Well, there's a very simple technique that surprisingly works, and I hinted at it by saying, look at all the occurrence of everything that appears once, just call it unknown. What you could do is you could look at everything that could appear that hasn't appeared and treat their probability as being 1, and increment everything else by 1. So just add 1 to all the counts. And so all your unknown words appear once, and the words that appear once now appear twice, and the words that appear 3 times appear 4 times, and so you just increment everything. Okay? The first thing is like, that sounds like a hack, and I bet you it was for the person who first did it. Okay? But it's now being proven to be a surprisingly good thing to do. Okay? Because it actually gives you a chance to give the probability distribution of really low frequency things and of really, really, really low frequency things, and it's better, okay, than just ignoring them. It's much better than just ignoring them. So this add to 1 technique is a good thing to do, okay? Now, you can go a wee bit further instead of saying add to 1, and what you could do is you just add a little bit. Now, we've been talking about getting the counts of words, okay? And counts, as we would imagine, are really all integers. But we don't care about that, and we could just add 001, and we could say that this word appeared 0.001 times, okay, so a non-integer amount of times. We could still generate probabilities out of that. You could say we could multiply everything by 1,000, and then we'd all be counts, but you're not going to do that, okay? And so what we could do is just add a small number rather than 1. And then once we can also do that, it's like, maybe I could guess what that number might be and might have a better guess of its distribution rather than just treating everything that hasn't appeared as being 1. I could actually make some other piece of information about it. So for example, I said in Wall Street Journal, numbers may have only appeared once in the Wall Street Journal. We don't really think of them as words, and we don't really sort of care about it. Maybe we should just replace them with the word number, because it doesn't really matter. But some numbers have got different distributional properties. You know, the numbers from 1 up to 31 appear quite a lot in dates. At the moment, 2019 appears way more often than what it did 10 years ago. And same with 2020, 10 years ago, okay? But at the moment, 2030 is pretty rare, okay? So we could work out something about the distribution of numbers, and there's this really weird thing about numbers. Most numbers start with a digit 1, which seems utterly, that can't be the case. But it's true. If you look at all the numbers that have appeared anywhere, there are more numbers that begin with the digit 1 than any other number. By quite a substantial amount. It's about 60-70%. Okay? And it's like, shouldn't it be, I mean, okay, zeros may be special, we won't count that, but 1 to 9, shouldn't it? No. And it's not exactly clear why that's the case. It might be that people are much more willing to talk about 10 and 100 than they are about 9 and 99, okay? Unless they're in a supermarket, and they're $9.99, okay? But it's just weird. But anyway, if you look at the distribution, starting with the 1 is much more. So you can actually do something about guessing what these distribution information is. Okay? And so this is a way to do it. Now, there's actually specific algorithms about doing this smoothing, where you collect all your stats, and then you want to change the numbers to make sure there's no zeros. Zeros are bad. You always want to avoid them. And there's this good algorithm called good Turing smoothing. Turing is Alan Turing, who I hope you've heard of, okay? And good is not because it's the good Turing smoothing and the bad Turing smoothing he decided not to publish. This is because there's another guy at the same time as Turing at Bletchley Park in the UK called Good. and I can't remember his name, but it's always identified by his initials. So let's say AJ Good. I can't remember what it is. He didn't use his name. He always used his initials. But he was one of the early computer scientists and has such a cool name. And I'd really like to do papers with people who are called Good, because then you get such a better name for the reference than what you normally get. Especially when you're somebody like me and you're trying to talk about, here's the good Turing technique and here's the black Turing technique. It sounds like it really sucks, or it's got some evil power or something like that. So, you know, don't have to be for that. But good Turing smoothing is a standard method from the 1950s. Okay, which is a long time ago. So we were doing language models, though they were doing it for biology distribution of, they were looking at distribution of butterflies or pigeons. No, it was Darwin that did the pigeons. I think they were doing butterflies. And what they basically do is they had to count everything. That's the fundamental technique that they're doing that I talked about. Okay, and what you can do is you can do a little bit more than that than just adding one to everything. What you can actually do is you can do this when you, especially with n-grams, you want to be able to smooth. You can have a technique that look at the distribution of the n-grams, and you can get a slightly better approximation of this. Okay, and it works pretty well. And even though it's from the 1950s, and even though we're all embarrassed to say it, this is hard to beat. Okay, for first approximation of smoothing, this is what you should do. There are better techniques. They're computationally much more expensive, and it depends on the amount of data you have. But this is a good technique. And almost all things that build n-gram language models will give you an option for good Turing smoothing. You're not going to be able to do that. There's another technique, because if you're trying to build a trigram or an n-gram model, and you don't have any examples, what do? And there's a good technique called back off, and that is if you've got trying to find the probability of a trigram and you have no examples of it, what you do is you just take the probability of the bigram, so you go from 3 to 2. And this is a good approximation, okay? So you just basically go down the shorter one. And so now, when you've got your really long n-grams, what you do is you're trying to find the probability of a sequence of 5, and it's now, you just look for the 4, and you can't find it, you look for the 3, you can't find it, you look for the 2, you can't find it, you look for the 1, then you have to care about some form of smoothing. Google, maybe even 10 years ago, released a 5-gram model for all of their data, all of the data they indexed, called All Your N-Grams Belong to Us, which is a meme, or it was a meme. It's everybody thinks it's great, and in various classes when we're trying to get data to build language models, people go, oh, download the Google N-grams, okay? And I have to remind them that the class only lasts 1 semester, and they probably won't be able to download it in the whole time of the semester, probably, okay? Because it's unbelievably huge, okay? They took all the data that they had in 2005, and even then the net was almost infinite, okay? There was still an infinite number of cat pictures in 2005, and they calculated the 5 grams for everything, and it's just useless. It's just too big, okay? They did show that they could, but you really just want the 3 grams, because anything more than that ends up being just so big that it becomes really hard to actually deal with. Around that time, one of our PhD students, Ken Heathfield, who's now a professor at Edinburgh University, was doing a thesis on how to use all this data, and he did a thesis on how to do optimal representation of massive language models, and he was doing massive terabyte language models back in the late 2000s, and getting substantially better results. Google was using his techniques. There's a thing called KenLM, after Ken, that allows you to get really super efficient representations of really large models, terabytes of data. And he does it by bit flipping, and he does it by compressing the things that don't really matter, because actually you don't care much about accuracy, you care about ranking, and so you can use that information to make decisions about how many bits you use to represent each of both the n-grams themselves and the probability information that you actually have. Yep, back off is the other one. So back off and smoothing are the most common ones to be able to do that. So what I've talked about today is estimating the probability of the word given some history. We talk about relatively frequencies. We do counts and normalize, so we're counting things, and then we want to be able to divide by the total number of words to be able to get the probabilities. We can do smoothing by this add one, or add some small number. Is actually called Laplacian, and it sounds better than just add one. Good Turing discounting is a little bit more, by looking at the distribution of the n-grams, you can get a better estimate of that one and change it accordingly. We can interpolate between multiple language models. I didn't talk about this, and that's something that's worth doing. So you can have a language model that's trained on all of the Google data, and then you have a language model that's trained on the data in your particular application, and then you can take the average of them, or the weighted average of them. Because the general one is really good when you're general, but the specific one is really good when you're specific, and choosing between them is always a good thing to try to do. So good Turing is a good way of doing it, and there's a thing called stupid backoff, okay, which is not named after Mr. Stupid, though hey, I could get that as a co-author as well. I do have a co-author with a Dutch colleague whose name is Joke. Her name is spelled J-O-K-E, which is unfortunate in English. But hey, it's a good, funny paper, it's a joke paper. But stupid back off is just basically saying, I'll take the next one down. It isn't actually named after Mr. Stupid. But there are more interesting ways of doing it. Kenizer now works at Amazon. Herman Nye is still at Arkham University. And so there are better ways, and depending on the data that you have and the amount of effort you want to do, these can be better things to actually do. Okay, that's it for today. Are there any questions? We are trying to clear the wait list. We are sort of now interested in individual cases when it doesn't work, but it's probably because you don't have enough units.